Hello, this is your instructor, Tom Porepsky, and let's finish up Module 6 now on continuous random variables. And in this last section, we're going to take up what's called the normal approximation of binomial probabilities. Recall the binomial distribution that we covered in an earlier module. You should have noticed that as n increases, binomial calculations get harder and harder to do, especially by hand. Now, if you happen to have a good calculator or computer available, that makes it much easier. However, we're going to show you another way to approximate binomial probabilities as n gets larger. You might recall also that if p is a half in the binomial is symmetric, just like a normal distribution is symmetric. And you can show in mathematics that even if p is not a half, the binomial gets more symmetric as n increases. This gives us a chance to use the normal distribution to estimate binomial probabilities. Now, when would we want to do this? If n is large and the calculations would be too difficult to do by hand, and if we didn't have a calculator or computer around that could give us the exact answer. In general, to use this method, you should have n, the number of trials, to be at least 20, and n times p and n times 1 minus p should be at least equal to the number 5. Recall how we do normal distribution probability problems. We use the z formula to convert our x value to z and then look up the appropriate probability. Now what we want to do is sort of apply this to a binomial distribution. Remember, of course, that if x is a binomial variable, that the mean mu is equal to n times p, and the standard deviation sigma is the square root of n times p times 1 minus p. And we're going to use those in this formula in just a moment as the mean and standard deviation. However, I'm going to make a claim right now, which you're going to see in a moment. If we simply just straightforward applied the z formula as it is, we're going to get an underestimate, and we're going to need to correct for that. I'll explain that more in just a moment. I usually like to go with what I call a rigged example to show this. Let's take a binomial problem where n isn't too large, and we can get the actual answer either using a calculator or a table of binomial probabilities. Let's start with a binomial with n equal 20 and p equal a half, just like flipping a coin 20 times. And let x be the number of heads. Suppose we were interested in the following probability. We want the probability that x is at least 13. In other words, the probability of 13 or more heads in 20 flips. If you go to some binomial tables, or if you use your TI-84, if you have one, you should be able to find that the actual binomial answer here is 0.1316. Now, most of the time, we don't know these actual answers, but in this case, we do. Now let's approximate this probability using the normal distribution. First, we have to calculate the mean and standard deviation. 20 times a half is 10. 20 times a half, and taking the square root is 2.24. So we have a mean of 10 and a standard deviation of 2.24. So if we just treated this like a normal distribution problem now, we want x bigger than or equal to 13, we would convert that to a z-value. You would take 13 minus the mean of 10 over the standard deviation of 2.24, and you would get a z-value of 1.34. And you want all probability above there. If you go to your table or use your calculator, you will find the probability then would be about 0.0901. Notice that's not a very good estimate. We happen to know the actual answer, remember, is 0.1316. So 0.0901 is not really that close to 0.1316. And we have an underestimate. First, I'm going to explain to you a little bit about why we have an underestimate. Although you really don't need to worry about the theoretical part, I'm going to do some explanation anyway. And then we'll show you what we can do to make it a much better estimate. The reason we're getting an underestimate is we're using a continuous curve, the normal, where probability is area under the curve, to estimate a binomial where probability occurs at individual points. For the binomial, for example, here, remember the mean was 10. You could get 10 heads out of 20, or 11, or 12, or 13. Probability occurs at those individual points. Notice if I did the following. Supposing I said for the binomial, take all probability from 12 on down, and all probability from 13 on up. If you think about it for a moment, those two probabilities have to add up to 1 for a binomial. Think about flipping a coin 20 times. You either get 13 or more heads, or you get 12 or fewer heads. That's the entire distribution. But notice if I use a normal curve, and I take all area less than 12, everything below 12, and all area above 13, something got left out. The area between 12 and 13 has been left out. We have sort of a gap in the distribution. And in a sense, that's why we got an underestimate. Now, we can solve for this underestimate problem by using something called the correction for continuity. We're going to take that 1 unit gap and put half of it with each of the two probabilities. In other words, if we want x bigger than or equal to 13, we're going to enlarge the area by going back to 12.5. If we wanted 12 on down, everything less than or equal to 12, we would enlarge it by going up to 12.5. In that way, that 1 unit gap between 12 and 13 is accounted for, and the estimate gets more accurate. Let me also point out at this point that if we were doing a different probability, say we wanted 13 less than x less than 18, so we have two values, we would have to use that half unit correction on both sides of the distribution, or rather both sides of the equation. In other words, we'd have to take everything from 12.5 to 18.5. If I were to redraw the graph that I showed a minute ago, in a problem like this, you actually have two gaps in the distribution. So, let's go back to the problem we were doing and apply the correction for continuity. We wanted the probability that x is at least 13. We know if we just solved for it the way it is, we will get an underestimate. So we enlarge the area by half a unit and take x bigger than or equal to 12.5. Now convert to z like before. Take 12.5 minus the mean of 10 over the standard deviation of 2.24. Now we get a z-value of 1.12. If you go to your z-table or use your calculator, you will find the probability that z is above 1.12 to be 0.1314. Very close to the actual answer of 0.1316. So if you're doing a normal approximation of the binomial, don't forget to use that correction for continuity. Now, students often have a very hard time understanding, when do I use this normal approximation of the binomial? Well, on some problems, the problem might just tell you use the normal approximation method, but on other problems, they might have you kind of figure that out. The thing to remember here is nowhere in the problem does it say that you have a normal variable, because you really don't. You have a binomial variable. But n is going to be large enough that you really don't want to be using the binomial formula and converting it by hand. If you wanted to figure out the probability of 60 or more heads in 100 flips of a coin, and you wanted to do that by hand with the binomial formula, it would take you probably hours and hours and hours, if not days and weeks to do. You'd have to calculate f of 60, f of 61, on up to 100, and add them all up. So generally, when you have a large n value for a binomial problem, is a good time to use the normal approximation method. Let's do one more problem, one more example. Let's say in a community college, 40% of the students go on to a four-year university after graduating. If we take a sample of 100 students, what's the probability that 30 or fewer go on to a four-year university? Now, if you think about it for a moment, students either go on to a four-year university or they don't, two possible options, much like the binomial. So we basically have a binomial here with 100 students, n is 100, and we want x to be 30 or less. x less than or equal to 30. If you wanted the exact answer, you'd have to go back to the binomial formula and calculate f of 30, 29, 28, 27, all the way down to 0, and add them all up. Or hopefully you'd have a calculator or computer to do it. But let's assume that you don't have any of those available to you. Let's just use the normal approximation method to approximate the answer. We want the probability that x is less than or equal to 30. First, you have to use the correction for continuity, that little half-unit correction. We enlarge the area to be 30.5 and below. So now we want the probability that x is less than or equal to 30.5. Then you have to calculate the mean and standard deviation of the binomial. Remember, the mean is NP. In this case, that would be 100 times 0.4 or 40. The standard deviation is the square root of NP times 1 minus P, which turns out to be about 4.90. Now you're ready to convert to Z. Take x less than or equal to 30.5. That has to be equivalent to Z less than or equal to 30.5 minus 40 over 4.9. And that gives you Z less than negative 1.94. Go to your Z table, and you will find a probability of 0.0262. So the probability that 30 or fewer of these students go on to a four-year university in a sample of 100 is 0.0262. By the way, I figured out the exact answer on my calculator, and the exact answer here would have been 0.0247, pretty close to our 0.0262. So the normal approximation method can give you a pretty good approximation of a binomial problem when n is large. And that's the end of Module 6. And in Module 7, we will go on and learn some things about sampling and sampling distributions.